Hi, everyone. Welcome to Quantum Conversations 12. It's been a while since we had a session, so we had like a very long summer break, I guess. Today we'll have speakers from Bleximo, and we have a tradition of everyone introducing themselves at Quantum Conversations, as this is a discussion platform more than a speaking series. So I'll start, and if everyone can like say where they're coming from, I mean, where they're physically located right now, and their name, and then why they're interested in this session or maybe quantum computing in general. So I'm Mert. I'm at Oxford right now, the cafeteria of the physics building, and yeah, and I'm interested in quantum computing more academically, I guess. I'm studying it right now for my PhD. And I worked with Fabio before. We were at QC Ware together. And yeah, that's how we started this talk. So Fabio, do you want to introduce yourself?
Yeah, happy to. So, hey everyone, I'm Fabio Sanches. I'm currently the head of quantum engineering at Bleximo. Like Mert just mentioned before, I was at QC Ware for close to 4 years. Joined there, in between their seed and Series A round, and left shortly after their Series B. So QC Ware was a software company for quantum computing. Now Bleximo is a quantum computing hardware company. So I'm happy to kind of discuss more about what Bleximo is doing. I'm based in San Francisco, but I'm physically in Seattle right now. And I guess I'll pass it on to Ziggy to introduce himself too.
Hey guys, I'm Ziggy. I am a mechanical engineer. Got my undergraduate degree at Harvard and spent a couple years working in the medical device industry. Currently, my title at Bleximo is cryogenic platform lead, and I work a lot with all kinds of hardware in the company, based in the San Francisco Bay Area, and excited to meet you all today. Thank
you. Alexei. So Alexei started the Quantum Conversation series, actually, so you want to go, Alexei?
Yes, thanks, Mert. So I'm Alexei Krabrov. I'm currently technical ecosystem development lead at IBM. I started at IBM Quantum, and now I'm at a new team called Accelerate Discover, which spans AI, HPC, high performance computing, and quantum, kind of crown jewels of IBM to incubate new projects and basically become kind of a bridge between, research and industry. Currently, I'm actually working on communities for the future scientific platform, which will enable researchers, big labs, to kind of use state-of-the-art things we take for granted, data science, community, like online model storage, collaboration, stuff like that. So and obviously, quantum is one of the important areas of this, and I'm looking at kind of how scientists work and collaborate everywhere in physics and chemistry and everywhere else. And I'm really happy that quantum computation continues under Mert's leadership. So great to see all of you guys. I'm located in Oakland. It's beautiful and sunny, the land of eternal youth and sunshine, and it's still wonderful here. It's a summer, so good to see you guys.
Thanks, Alexei. Jeremiah.
Hey everyone, I'm Jeremiah. I'm a PhD student at Princeton University. I'm in the electrical engineering department, and I plan to join the HAUC lab, which is the superconducting qubit lab. And so that's, I guess, how I'm interested in like the superconducting hardware startup like Bleximo. Yeah, that's me.
Cool. Yeah, Jeremiah was a president to Stanford Quantum Computing Association last year, and we're also partners with them, as I went to school there, like Santi did. Hey, Santi.
Hey, what's up? Santiago. I'm currently in Mexico City. I studied physics at Stanford, and now I work in quantum computing software, specifically for finance. Glad to meet y'all.
Thanks, Santi. Abiskar. Abiskar has been coming to our sessions from before as well.
Yeah, hi everyone. My name is Abiskar. I'm joining from Nepal and I'm high school graduate. Currently, I'm in gap year. I'm planning for my undergrad, maybe somewhere, I don't know where I'll end up. And currently, like I'm working since 9 to 10 months in an initiative in Nepal called One Quantum Nepal. And it's a chapter or wing of One Quantum Global. Yeah, that's all.
Thanks. Kiran?
Yeah, hi everyone. I'm currently from India. So thanks to Alexi and Mert, I've joined since starting in QC conversations, and probably since my undergrad I was interested in QC, and since then I've been taking up some projects and trying them myself. So it's quite interesting. Thank you.
Thanks, Kiran. Hi, Brent.
Hi, you said Brent, correct?
Yeah.
Okay, so my name is Brent Lunsford. This is my second time to join you guys. I'm currently located in Austin, Texas. I'm the president of Memstronics. So most of my career is spent on MEMS and sensor technology, but I started my career in 1995 working on artificial intelligence, high performance computing, and what we called back then massive parallel computing. I'm also the founding officer of the IEEE San Francisco Bay Area MEMS and Sensors chapter, and the founding chair of the similar chapter in Austin, Texas. I also serve as the global engagement chapter for the IEEE Sensors Council. One more thing I want to mention. We're working on having an industry roundtable in Austin, Texas, where we're going to establish standards for sensor technology. If you think about the future of autonomous vehicles and drones flying all over the city, we need to put some standards around these technologies before we just launch them out in the commercial market. So I'll stop at that. If anybody wants to reach me on any of these topics, just let me know and I can shoot my email or I'll just share it with everyone. Thank you.
Thanks, Brent. Borsan Alsano.
Hi everyone, my name is Baujan. I'm software engineer in finance. In previous position, I was cryogenic engineer, so I have a little experience with cryogenic facility and some quantum detectors. Now I will try to increase my software skills by using QC tool. Yeah.
Thank you. Yeah, so we actually have like a document on our website that has resources for like the tutorials and like textbooks and all of that for like, for example, if you want to learn Qiskit, you have a specific goal in mind regarding quantum computing. You can look at that document. It's really helpful. We had a session on like educating yourself in quantum computing. But Alexi, that document is like buried down in the website. I need to like get it up somehow. Okay. J Power. That's the name I see.
Hi.
Yeah.
Hi, can you hear me?
Yep.
Hi, I'm June. I'm actually not a black box. Hi.
Cool.
I'm in Palo Alto and I'm thrilled to be part of this. So thank you, Mert and Alexi. And also this is an interesting talk for me because I did some quantum mechanics at Berkeley when I was an undergraduate there. I'm in Palo Alto, a lot of Stanford connections. And I also was at Oxford for a time. So
Okay.
I was invited and connected to Balliol College. So it's very cool to be here. And I guess the best way to describe myself is quantum curious. So hi, and I'll go dark again.
Okay, thanks, June. Hey, John. Nice to see you again.
Yeah, nice to see you. John Candelaria, I'm at Stanford. I am working on a program here called System X. And last year I was working with the Quantum Economic Development Consortia, the QEDC. And it looks like Stanford will be rejoining that, fortunately, after a while away. So I might be engaging with him again soon.
Thank you. Hi, Jamie. Are you back from New York?
Yes, hey Mert. Yes, I'm back. And yeah, shout out to everybody in Silicon Valley and everything too. I'll actually be in California for the first time in a while next week for Q2B. So totally, if anybody else is there, totally give me a shout out while I'm in town. And yeah, right now I'm doing graduate classes at Wisconsin-Madison in quantum computing.
Thanks. Yeah, so there's a Q2B, there's a conference next week, Quantum to Business. QC Ware is organizing it. So I'll be there as well. I'll be in the Bay Area. Santi will be there as well. So if anyone's around, I would love to meet up. Veso.
Bleximo will have a booth, so stop by.
Okay, perfect. We'll stop by.
Yeah. Hi, my name is actually Veselin Georgiev, and I'm sending my contact information like LinkedIn. I'm in California, mostly Northern California in the Bay Area. And I'm mentoring for Quantum Open Source Foundation and QWorks. So if any one of you is interested to work on their own projects, they're welcome to connect with me and give advice, apply to the Quantum Open Source Foundation program, and we can work together on a project that you may be interested in. So that's about me.
Cool, thanks. Thanks. Yeah, we had a session from someone from QWorld, specifically Q Turkey. Zeki was here like 2 sessions.
Was it Adam?
Zeki.
Oh, Zeki, yeah.
Okay. Jan. We can't hear you, sorry. You're not muted, but we can't hear you. Yeah, that's fine. We can come back to you. Ziyong.
Hi, everybody. This is Jungjung. I'm sorry, I have some problem with my video. Yeah, I'm at Stanford. I work at Stanford Research Computing Center, and I used to be a computational chemist, and now I'm interested in quantum computing. And my interest in applying quantum computing to quantum chemistry problems as well as machine learning problems. And recently we have a quantum learning machine, the machine for simulating quantum computing from atoms. So that's one of the other projects I've been interested in working right now. So that's about it. Thank you.
Thanks. Yoni?
Hi, I'm I work on physics of superconductors, and I'm interested in moving to doing something related to quantum computing.
Cool. Siddharth?
Hi, I've joined a couple of these sessions before. They're pretty cool. I'm an undergrad at UC Berkeley studying physics. I'm a part of the quantum computing club there, worked on a couple cool projects with D-Wave and IBM's quantum experience stuff as well. Yeah, I'm just really cool to be here. I like quantum computing. I think it's cool and I'm happy to learn.
Cool, thanks. Augusto.
Oh, hi. Can you hear me? Yeah.
Yes.
So,
nice to see you again.
Yeah. How are you?
Good.
Hi, Mark. Hi, Alexei. I'm from Argentina. I'm a quant dev on some dedicated and some software engineering things on some enterprise thing. So yeah, mainly trying to learn bit by bit. the part of quantum don't want to miss out these things. So yeah, I'm here just to learn.
Thanks. Noor.
Hello everyone. So my name is Noor and I'm from Jordan. I have a degree in physics and right now I'm looking for an opportunity to do a PhD in quantum computing.
Okay.
Thank you.
And Tom is a student here, also at Oxford. He just joined with me.
Yep. Hello. Matt took my introduction away from me. Yeah, I'm a student at Oxford doing a PhD in physics, and I'm kind of interested in error suppression for like near-term quantum computers.
Thanks, Tom. And Jan, were you able to fix your mic or?
Can you guys hear me?
Yes, yes.
Cool. All right. So, hi, my name's Jen. I'm an undergraduate at Stanford, studying computer science, and I just recently started, I guess, becoming interested in quantum computing. So, I am also quantum curious.
Cool. Okay. Yeah, everyone's saying quantum curious. I wish Nathan was here. He has a website called quantumcurious.org. He loves to talk about it. But yeah, I mean, you guys can check it out. Yeah, thanks everyone for introducing themselves. I guess we can go ahead with the talk. I'll make you a host, Fabio, if you're gonna go first, or Ziggy, which if you have like slides to share, I can.
Yeah, I'll share some slides, and Ziggy will share some slides, and
okay,
then that's it.
Right. Here we go. Yeah.
Cool. Okay. I should be sharing it now. Okay, can everyone see it in full screen?
Yeah.
Great, thanks. Okay, so I'll give kind of a broad overview of Bleximo. And then Ziggy will talk more details about the actual hardware. So, for those of you who don't know, Bleximo is a quantum computing hardware company. We're located in Berkeley. And the technology for which we use to build quantum computing hardware is superconducting qubits, just like IBM, Google, and Rigetti, right? So we are early stage, where we've raised a seed round recently, but we will be getting kind of our kind of first DIL fridges that we own starting next year, and we want to deploy things on the cloud hopefully by the end of next year. But we're not just building generic quantum computing hardware like Google, IBM, and Rigetti. Our approach is slightly different. Instead, what we want to do is essentially focus on application-specific chips and everything else around it, right? So it's more than just a chip, but also like compilation techniques and gate design and so on. All of that, instead of building it for a kind of a general purpose and kind of looking, 15 years down the line, instead we want to see how much can we optimize these systems by kind of narrowing their focus. That's not to say that they won't be universal quantum computers, of course. That's not a very high bar, right? So long as you can get some entangling gate and single qubit gates, that's universal. But the point there isn't really to do that. The point is to really kind of build a framework, first of all, so that application-specific devices make sense to build, and we have a kind of a system for doing so, and then getting as much performance as we can for specific applications by going down that path, right? So really what we're trying to do is build quantum solutions on application-specific hardware. So kind of our mission is to deliver quantum advantage for useful problems by co-designing algorithms and hardware. That's kind of delivering quantum advantage. Probably every quantum computing company has that goal. So there you have it. But our approach is really to kind of look, start with an application and then understand what algorithms make sense to apply to that application, and then understand the structure of those algorithms, even more than just kind of a generic algorithm, but as applied to that specific application, and then keep going down the stack until the actual kind of chip layout. So, here's kind of a generic slide on quantum computing, right? So the whole goal of quantum computing isn't just to be a faster processor, but it's instead to address computational problems that are hard classically, because that's where there's some hope for quantum algorithms to kind of deliver an advantage. So here's kind of 4 problem classes that the community has been focusing in the past few years, right? So quantum simulations, that's for chemistry, pharmaceutical materials, like any quantum systems, we already know that there exist algorithms for which it is more efficient to simulate them on a quantum computer than a classical computer. Optimization, well, lots of optimization problems are hard to solve classically, at least exactly. So for those hard problems, there is hope that quantum computing heuristics might do better. I'm not, I always make it clear that it's not like quantum computing can solve NP hard problems efficiently. That's not the case. But there is some early work already on various algorithms for which there could be a chance for quantum computers to outperform classical computers. So Monte Carlo simulation, the kind of self-explanatory. It's used very often in finance for derivative pricing or risk assessment. We do have a quantum algorithm that speeds up Monte Carlo simulation. And in fact, there's been kind of a lot of work over the past 2 years on making that algorithm kind of simpler in many ways to have a potential to run it on even noisy devices. And then machine learning is, of course, a huge area classically. There are various quantum algorithms that address various portions of machine learning. Of course, there's lots of issues with those, so it's not clear whether or not this is a near-term area. But because it's so important, it's useful to keep looking for algorithms that might provide an advantage in machine learning capabilities as well. Okay, so this is where we are. We're kind of in what's called the Nisk era. Nisk stands for noisy intermediate scale quantum. So noisy kind of speaks for itself, right? So the quantum computers aren't perfect. They have errors. They decohere. So their coherence time is limited, so is their gate fidelity, which really means that you can only run an algorithm of a certain depth, meaning you can only apply so many gates to the device. We're working with hundreds to thousands of qubits. We're not quite at the hundreds mark. There's a group in China, I think, that currently has the record on the biggest problem really run on a generic quantum computer. D-Wave still has 5,000 qubits, so but that's not a generic quantum computer. But the point is with Google and the experiment in China, we've seen that that we already have, even with like 55 qubits or so, we already have power that's kind of beyond classical in a way. So, but what I mean by that is that we can't simulate these, at least for random circuit sampling, we can't simulate it classically. So the question is, are there other applications for which they run better on these Nisk devices? So this is the era that we're at. There's no concrete answer to that question. We don't know whether that there will be an advantage for various industry applications on these devices, but certainly that's what the community is focusing on. We know that once there's error correction, there's all sorts of algorithms that make sense to run. Okay, so the question though is why co-design? So by co-design, we mean really kind of designing hardware and software kind of together. And by software, I mean algorithms and applications, right? It's more than just kind of a user interface. So first of all, I want to point out, and as I already have, that quantum computing is an accelerator, right? So we don't envision, for a while at least, maybe who knows in 100 years, but we don't envision that quantum computers they're going to replace classical processors. So instead, they just perform certain tasks really well, right? So quantum gates allow us to manipulate the device in a different way than classical computers can. So just like GPUs are good at doing certain things like matrix multiplication, quantum computers are going to be good at other things. So they're only an accelerator for certain problems. So they're kind of already application specific, just by phrasing it in that way. So the other important point is that for anyone who's tried to run something on current quantum computing hardware, you can very quickly see that a generic implementation that just uses generic tools, like even if you program it at the circuit level, but you don't use native gates and all that, and you run a generic compiler, you're not going to get good results out. And partially that's because the hardware is very early, but the other reason is that all these tools, they kind of incur overheads that you lose track of unless you're really kind of going down to the hardware level. So for there to be kind of a good chance of running something non-trivial on a Nisk quantum computer, we really need to think about kind of hardware specific designs for algorithms, or you can think about it the other way, design hardware also that is amenable to certain algorithms. So we also need just a lot of improvement across hardware and compilers before we can use these generic tools across various algorithms and various devices. So these tools already exist, right? You can kind of transpile between devices, you can compile down to native gate sets, all these tools exist, but it's not clear that these are the tools that one should be using in the near term. And then, the last point is that even with fault tolerance, obviously the architecture is really important, and depending on how you design that architecture, you can get kind of non-trivial performance advantages on running even fault tolerant devices. Okay, so the idea is essentially to use qubits and quantum operations as efficiently as possible, and also so that's kind of going from the algorithm level, and then from the hardware level, it's like by focusing on application specific tools, we can maybe reduce the engineering burden to kind of improve hardware, right? Because we only need to improve it in a more specific way. Okay, so here are some tools that one might envision using, right? At least on the software level, right? So there's compilation, in which you can commute gates, you can kind of change the native gate set in certain ways, but there's these tools already exist, but the idea is that we have to compile to specific hardware. And how do you do that in a way that's very efficient? Well, our approach is essentially to narrow it down to specific applications first. So kind of work with the high level application algorithm, keeping in mind what the architecture that we have is. And then another thing that can be done is, to design the gates, we need to kind of, what we typically do is we have a certain pulse, right? A microwave pulse that controls the qubits. And typically, we know what these pulses are for certain gates. In principle, there are different observable control techniques, or some companies use even like reinforcement learning to try to design pulses that are more that have fewer errors. One can imagine kind of optimizing pulses as well for applications, for certain specific applications. Okay, so what are some other advantages of kind of going this co-design approach? So the first is that if you're just kind of working at the algorithmic level, if you're a business and you want to know, okay, what quantum algorithms are there for my problem, and when is this going to give me an advantage? Well, if you're working at a really high level, it's going to be really hard to answer that question precisely. So even if there is a chance for kind of an advantage in the near term, without narrowing down to a specific architecture and understanding the errors and so on, you're not going to get an answer that's kind of precise enough, maybe to within let's say 2 times the number of qubits that you currently have, or whatever error rate you are predicting. So you kind of need to know what architecture you're working on, or you're not going to get that information. Another advantage is, of course, that generic hardware is never going to be fully optimized for your use case. And like I mentioned before, kind of because of the errors that we currently have in the Nisk era, it's really important to optimize gate design and hardware layout for specific applications. And then another advantage that is probably very important for enterprise customers is that it's much more defensible, essentially, to kind of have IP that incorporates hardware designs as well. So that's another advantage for businesses there. Okay, so I want to kind of just point out one specific application, right? So this is kind of a Monte Carlo application that I mentioned earlier, right? So on the left, this is just a figure from the paper that shows kind of what kind of gates are being implemented on that algorithm, right? So we kind of have these 3-qubit gates that are controlled rotations with 2 qubits of control. And this is straight up from IBM, right? So this is kind of what the decomposition of a specific gate looks like. And you can see that, like, one 3-qubit gate becomes 5 2-qubit gates here. And then each of these 2-qubit gates, actually, when you compile down to hardware, would have already 2 more kind of controlled Z. So those would be maybe the native 2-qubit gates. So all that's kind of hidden here, right? But each of these 2-qubit gates is kind of incurring like a pretty bad error. So you only have a limited number of them. So to really analyze it, you kind of have to go down to the native gate set for the hardware. And this is very generic here. I'm not even analyzing this algorithm. I'm just pointing out that this is an issue. And in addition, even this isn't taking into account the connectivity. So it's not clear that qubit 1 is connected to qubit 3 here. If that's the case, then you need to do a swap, and that's going to incur another, at least 3 2-qubit gates or something like that. Okay, so I'll transition over to Ziggy, but in order to do that, I just want to mention that, Bleximo, is working on co-design, but we also really focus on designing really good kind of packaging and shielding and, kind of processor layout for the chips that we design. So here's an example. This is in partnership with AQT at Berkeley. The same chip was cooled down 4 times in different kind of environments, and you can see that the fourth cool down, which was with Bleximo's packaging technology, we get kind of an order of magnitude higher coherence times, right? So it's very clear here, and we're reaching coherence times of like 100 microseconds, which is on par with IBM's processors. So this is for 8 qubits. Here's again another kind of just kind of data on the coherence time for, this is just on one of the qubits, but you can kind of see that we're reaching the limit for T1 and T2. And finally, I'll actually end with this video, which is kind of showing how one would design a chip. This is kind of what we do here, and we start by designing a chip and then analyze all the modes there to try to like minimize crosstalk and things like that. This is a video done by Kiara. She's our microwave engineering lead. Just takes about 40 seconds or so. This is just a 4-qubit chip to clarify. So we essentially you know, kind of play around with different designs. More than play around, we kind of study them carefully to understand you know, how to get the best performance. And that's one of the really important tools if we're thinking about kind of deploying this for specific applications, right? So then we can, by understanding exactly like, you know, what different parts do and how to lay them out correctly, we can kind of trade off between things that one might want in one application and not in another. So I'll end here. Thank you. Feel free to reach out, and you know, I'm happy to answer any questions now or at the end as well.
Yeah, I mean, if there are any questions now, you can go ahead and ask, or like anytime during the talk as well.
Yeah.
Just like shout out your questions. Otherwise, we can move past.
Yeah, I have a quick question. I guess well, thank you for the presentation, by the way. That was really, really cool. What I guess like type of qubit are you? I guess like, do you have like one type of superconducting qubit you use, like a transmon or like a fluxonium, or does that also change depending on the application?
In principle, it could change. I mean, we're studying transmons right now, and we have, you know, capabilities in fluxoniums, but we don't have kind of our generic like Bleximo's hardware deployed yet. So I'm not going to commit to a specific type at the moment, and we have the capabilities to build, you know, a few different types. But until we deploy our, you know, I won't commit on video to what type of hardware we'll deploy right now.
That makes sense. Thank you.
Yeah.
Hi, this is John. I had I guess a clarification question for you here. This is really interesting and great work. So from what I understand, I guess when you're talking about application specific, you're actually talking at least initially about, you know, starting with a specific class of algorithm, right, that would be applied towards a particular problem. And then once you have chosen that class of algorithm, then you design your hardware to optimize running those kinds of algorithms. Is that basically how it goes?
Yeah, that's basically it. It can be even more specific than a generic algorithm. For example, say, because VQE is I think of VQE as more as like a kind of a collection of algorithms. But you know, if we are thinking about VQE for a certain molecule, then it will be even more specific than that, right? Like what type of like ansatz that addresses like a certain class of molecules, maybe we'll focus on that, because that's going to be a little bit more specific on what type of gates and what connectivity we would be looking at. Does that clarify?
Yeah, okay, great. Yeah, and you mentioned connectivity. That was going to be my follow-up question. So I'm assuming it's obviously not just designing the, you know, the optimal qubit itself per se, but it's really the connectivity that you have to use to optimize running those particular algorithms, I guess, you know, and that's obviously a key part of it too, right?
Yeah, exactly. I mean, of course, you know, it would be great to have all-to-all connectivity, right? But we're not working with ions here, so that's not possible. But you know, kind of short of that, what can we do to, like, you know, have as high connectivity for, or you know, depending on the structure of the material, maybe, you know, you probably don't need all-to-all anyway, but you know, can you maybe mimic it as closely as possible to minimize swaps within reason?
Okay, thank you.
Hello, am I audible?
Hey.
Hello.
Yeah, go ahead.
Yeah. Like you've shown the design of the chips that you are trying out, right? And how close is it to real world problems, you know, that we can now like we are having classical computers, right? So how soon can we use these chips for solving problems, using quantum computers, real quantum, that way? And like you mentioned, it is more accurate than or than IBM Q. Could you please brief on that?
Okay, so yeah, let me clarify. First of all, I'm mentioning that the coherence times are on par with a lot of the latest IBM Q devices, specifically the coherence times, just to be clear. I have not made other comments about other aspects of the chip.
Yeah.
And then to answer your first question, there's no way that we're going to make one chip and it's going to have better performance than like the 50 or 60 bit of deploy an application specific chip that solves kind of a toy problem. And I'm thinking that, that could be anywhere between like 8 and 60 qubits, something small, but that's feasible. So kind of step for that, from that chip, you want to kind of scale it up and just, push for that to an advantage. Then that's way further out. That's way further out, right? So I'm not going to make any comments on how it's going to take, because that's also depends on specific applications. In terms of our roadmap, in 1 year we'll have like 2 qubits, and then scale up from that. The scaling up part kind of depends on what things we're going to focus on. If your question is like, when can you run something quantum on our chips?
Hello. Yeah. So my question was like, how close are we to use these chips? Like that way. Are we really in a position to use these chips for real like problems, or we are still far from, or these are just problem based, like you mentioned?
Oh, sorry. Maybe my audio cut off. Can you guys hear me? Okay.
Hello.
Hello. Can you hear me? Okay.
Yeah.
Okay. So, the question of when is quantum going to outperform classically for various problems, that we can be discussing this for like years. I think we'll see when that happens. So let me answer a little bit more specifically. Like, when can you like kind of work on our chips? We'll have our chips deployed in a year, but that's not going to like solve problems better than classically. We have yet to see like any quantum chip do that. So we'll probably need at least a couple hundred qubits. That's my personal opinion. If you want my opinion, that's my opinion.
What's the qubit count? Yeah, sorry. What's the qubit count right now that you're implementing?
Well, the biggest chip we've deployed is in partnership with AQT with the 8 qubits that I showed. That's Bleximo.
Yeah.
The biggest chip that's out right now is the one from the Chinese group that did random circuit sampling.
Yeah. Cool. Thanks a lot.
Any other questions?
Yeah, so for these chips, do you have like an approximate idea of what error rates look like and how accurate these are?
Well, so our goal is to for the first generation to kind of match the error rates for certain 2 qubit gates to kind of state-of-the-art superconducting platforms, right? So you can look at IBM's latest devices, like that's what we want to get to. We have research that's possible, but we haven't deployed anything on the cloud, and I'm fully aware that that's a different beast than doing something in a lab. So if you want the numbers that I'll commit to, like trying to achieve on the cloud, those are the numbers for the first few generations, really just kind of on par with what IBM is doing. And then after that, the kind of next few steps are going to kind of depend on clients and so on, and what things we're going to focus on.
Okay, I see. And have you tried implementing any like error correction codes or anything of that sort, like doing some sort of correction for the algorithms that you're trying to run, or is it just direct implementation?
Yeah, so we're not doing any error correction codes. That's not our focus even early on. Error mitigation schemes and things like that, yes, we will do that.
Okay, I see. Yeah, thanks.
All right, thanks, Fabio, for the presentation, and thanks to everyone for the great questions. I guess we can move on to Ziggy now.
Great. So I should somehow make him a host, right?
I mean, if he's sharing slides, yeah, I think so.
Hold on.
Yeah, can I just share my screen now? Will that work?
If it works, then it works. Otherwise, I'll make you the host.
Okay. Yeah, disabled, it says.
Okay, hold on, I'm doing that. Okay, I just did it, so you should be able to do it now.
All right, I'm the host now. Give me 1 second. So, hey guys, my name is Ziggy. Thanks, Fabio, for giving everyone the lowdown. I was talking with Fabio a week or two ago, and he asked me to join today so that I could give you guys an idea of what like the physical hunks of metal look like that we're actually using to kind of implement all of this like really high level theory stuff. You've seen pictures of like the chips. Fabio showed a picture of like a little box the chip goes into packaging wise. And today I want to share with you guys what the entire system looks like, kind of, when you walk in the room, what do you see? So let me share my screen real quick. Can you guys see this all right? Let's see.
Yeah.
Yeah,
cool.
And it's full
right.
screen now.
Great. So this is sort of a earlier draft of what you guys attending Q2B might be seeing if you stop by our booth. This is me with some of our systems. On the left, this Blue Force XLD fridge. On the right, it's a Blue Force LD fridge. You guys were talking about, how this is superconducting circuits. So how do they become superconducting? Well, they need to be very cold. And the coldest commercially available cryogenic refrigerator is called a helium dilution refrigerator. The type of helium dilution refrigerator that we work with is produced by Blue Force, which is a Scandinavian company. Their fridges come in 2 different sizes. XLD, extra large diameter, is on the left. It's about 2 feet in diameter. It hangs on a frame that's about 10 feet tall. We sometimes joke that it looks like a steampunk chandelier. It's got all this shiny gold. It's got a lot of beautiful metal, just gleaming at you. And on the right is the LD, the large diameter fridge, which is kind of ironic because we call it the small fridge, colloquially a lot. But anyways, the topmost plate here, I'll create a little laser pointer here. So you see that it looks like a chandelier because there's a lot of plates that are connected by these support struts, and every plate gets progressively cooler. The topmost one is exposed to the room environment, is at room temperature, and then there's different types of cooling processes that get you down to successively lower temperatures. So first 50K, then 4K, 1K, 100 millikelvin, and then the last stage is 10 millikelvin. And as you go down, the cooling power of each stage gets less and less and less until you're down into like nanowatts of cooling power at the 10 millikelvin stage. And for those of you who are interested in learning about helium dilution, it's very interesting. You mix helium-3 and helium-4 together, and it produces some sort of strange quantum cooling effect. It's honestly a little bit out of my wheelhouse, but you guys should look it up. It's really interesting stuff. And also another interesting thing is that this isotope of helium that you use to do helium dilution, it can only be produced through a weapons grade plutonium program. So you need to have connections with people who can produce this byproduct of that can produce this helium isotope. It's very expensive, comes in these little orange canisters, and you handle it very gingerly, and there's a whole room full of equipment that's designed to handle this tiny amount of gas very carefully so that it never gets lost, it never gets released into the room. It's not poisonous, it's not dangerous, it's just really expensive. And nobody wants to go through the hassle of trying to get more helium-3 gas. So a lot of time and energy is spent you know, trying to conserve that and getting it in sort of this nice closed loop in the system. Anyways, a lot of the work that I do at Bleximo is revolving around this machine that you see here and all of the parts that bolt onto the 10 MK plate. Really, it's fancy heat sinks. The mechanical team's deliverables to like the bigger picture of the company is increased coherence times and reduced iteration times as far as like between setups. One of the big ways that we increase the coherence times is through better thermalization. So when you bolt, so looking at this picture right here, at the very bottom, this box is, that's the same box that Fabio showed you guys a picture of earlier, and inside of that is the chip. But if you're focusing on all the hardware outside of the chip, it's a lot of metal parts that are bolted together. And the harder you can clamp them together and the flatter those mating surfaces are when you clamp parts together, the less impedance there will be for the heat to flow across that boundary. So your parts are going to end up getting colder if you clamp them more, and if you get a flatter surface, you get a better surface finish. And the colder parts means less noise in the system. That means higher coherence times. So a lot of the work that we spend, that we do, and the mechanical team is spent making sure that we can get the biggest fasteners that we can, as many of them as we can, clamping all of the parts that are in the heat path between this plate and the chip down there. Another aspect of what we do is shielding. There's shielding for like all kinds of different radiation. There's magnetic shielding. Everybody has a lot of different opinions on what kinds of materials shield better than others. If you can create a shield that's longer and skinnier, the aspect ratio ends up helping you out. And right now you're looking at 2 different RF components on this flange. The deeper they are inside this cylinder, the better you'll be able to shield them from like stray magnetic fields going on. The other aspect that really, well, I'll get to another slide and talk about the other aspects. But anyways, I'll show you guys a little bit. What's going on here? There we go. Okay, yeah. So I was talking about weight reduction. You know, we spend a lot of time creating these like very intricate geometries. Another industry that has sort of a similar need and similar application to us is aerospace. In aerospace, every pound of metal that you put into a system is going to cost you like $10,000 in rocket fuel and operational expenses and everything. So if you can reduce the weight of a part by 30%, but it increases the part's cost by 10%, you'll still go for it because it's worth it to have that extra little edge in performance. So you can see how we have all these really intricate pockets milled out on these parts, and that helps us to reduce the cooldown times for our systems. So in general, For bigger systems, like the one you see at the left here, it's hundreds of pounds of metal in this machine. All the metal that's bolted down onto this bottom stage is nanowatts of cooling power. So it takes a very long time to pump all the heat out of that thing and get it down to operational temperature at around 10 millikelvin. So we need to, for about every 1 pound of metal, it's about 2 hours of cool down time, more or less. That's the rule of thumb. So every pound of metal that we can reduce reduces the time it takes to cool a fridge down and gives us faster iteration times. So if people are working on, Fabio mentioned Chiara, our RF lead, she's working on a new chip. It's got a new like architecture that's optimized for some new algorithm, for some new client or whatever. If in order to swap out that chip into the system, you need to warm the machine up, then swap it out, then cool it back down, and reducing the time it takes to iterate on a new design. Let's just move faster as a company on a whole. What else here? We also, you can imagine these parts here, it's kind of a lot of work to like these start as a solid cylinder of copper, and then a machinist comes in and removes like most of the material to get these like very light structures that you can see here. Let's see. Another big thing we do is we work on jigs, and we spent a lot of time thinking about like design for assembly, design for service, design for maintainability. A big problem that we've noticed in a lot of like academic labs that are running fridges is that there's this term like we have called like grad student proof. Like sometimes there's like way too many people around a single fridge, all trying to screw in a screw from a certain angle. Everyone's bumping elbows. People are leaning on the fridge. People are getting their fingerprints in the fridge. It's kind of a fragile structure, the whole thing. So the more you can design this system to be assembled on the bench and to be modular and to have elements that come off the fridge and like very easily to quickly swap things out, the better. So my previous experience in medical device design, I was basically building machines that were about this size and complexity, but it was all like pumps and valves and fluid lines. But this is pretty similar. Instead, it's like shields and RF components and RF lines. But across any industry, you look anywhere in aerospace, in like maritime architecture, and in quantum computing, like you always need that like eye towards serviceability, so that you're not like getting bogged down, like completely disassembling the thing and then reassembling it every time you want to make a little change and iterate on your design. Another thing that we focus on a lot is materials hygiene. So maybe some of you guys who've worked with this, who've worked like kind of in the lab on a cryogenic setup before know this, but a single fingerprint in the machine is going to add in all these organic compounds that just don't thermalize properly and end up adding a lot of noise into the system. And then likewise for any like impurities in the metal, especially iron impurities. So we make sure that all of our stuff is made out of the highest purity commercially available copper, which is also the hardest to machine. So it adds some like manufacturing complexity in that sense. But this if you start using kind of like less and less pure grades of metal, you're going to have to make sure that those types of metal are further and further away from the qubits, or else you're going to start seeing a lot of noise injected into your results. The other thing that can help a lot is gold plating parts. So on the left or on the right, you can see some of the same parts that have been gold plated. If you touch copper with your bare hands, which is very easy to do on accident, the oil in your skin oxidizes on the surface of the copper, and if you touched it on one of those surfaces that's like a bolted joint between two parts, then that's going to reduce, that's going to like add resistance across that joint for the flow of heat across it, and ultimately the part's not going to get as cold, and then more noise in your system. So If you're willing to pay the price for gold plating, it's usually recommended because any stray fingerprints don't oxidize on the surface. The soft gold plating on the surfaces that bolt together also kind of fills in the cracks on the microscopic level and creates more surface contact for your bolted joint and just gives you like a better joint. In general, gold plating is like 2 to 5 times the cost of the part itself. Pretty expensive, and it's billed on like the market price of gold at the time. We work with some pretty intense industrial gold platers around here. Let's see. Another big aspect of what we do, I talked about like design for maintainability, design for serviceability. We make like IKEA style assembly drawings for all of our designs. So, there's a bomb here that's telling you every part that's in the machine. We have these beautiful like exploded diagrams showing you, which screw goes where. And this is something that we offer with all of our hardware. And is really, really important for making sure that you can get the design right. It's, right now, Fabio's mentioned that we're working with the AQT, Advanced Quantum Test Bed at UC Berkeley. We're also working with Lawrence Berkeley National Lab. And you guys will probably, you hear the whole spiel at Q2B if you're going there, but we're working on like selling this packaging to anyone who's interested. To kind of offload like the engineering challenges associated with making all of this hardware from like an academic machine shop to Bleximo's like engineering system, so that you guys can focus more on like the science and the theory instead of getting bogged down in a lot of these details like, oh, like what length screw do I need to bolt these 2 parts together? Where am I going to get that screw? We kind of have that all figured out for you in a big package. So that's another big part of what we do, is making sure that we're very organized and can kind of like be very flexible. Just hand someone a drawing and they know exactly how to put it together without needing a lot of coaching or getting an applications engineer to come visit you or whatever. Another big aspect of what makes for good hardware is rapid iteration. So we have this nice 3D printer, and we never commit to buying anything in metal until we've 3D printed it first and put it together on a bench. So that's one thing I'm pretty excited to start doing more and more of in the next year, is like doing more doing more rapid prototyping just to keep our designs like moving as fast as possible. Another big aspect of what we do, I mentioned with those drawings, is staying organized. Every part we deliver has a barcode, has a serial number, has all the information you want to know about the design right there on a label on the bag. Each one of these labels corresponds to an entry in like a cloud-based production tracking system that we have. Super essential for staying on top of exactly what's going on in each fridge that you have. So there's a big problem we've noticed where like a cool down happens and half the qubits don't work, and no one knows why, and no one knows what's even in the fridge connected to those lines that connect to those qubits, because there's like a million different people running around and no one is really like making a list of all the hardware that went into a machine. And this is how we keep track of all the hardware that we send to different people for different machines. So it's another, like, operationally, it's a big part of how we're trying to like stay on top of like troubleshooting for all of our designs. Another aspect that I don't have a slide for is, you know, a lot of times all of these designs are kind of like manufacturing driven. You know, when it comes to the thickness of each plate and how much material we remove and what kind of screws we use everywhere, that's mostly based off of our like industry experience with what a manufacturer might want to make for us. But in the coming year, we're going to be focusing more on like finite element simulations, trying to understand like exactly where the bottlenecks are in the flow of heat out of the system, and designing, like letting our designs be driven more by that instead instead of kind of like a manufacturing driven sort of approach, which is how most people do it right now. You know, Fabio might have mentioned that, so, you know, we're buying our own fridges pretty soon. We have a new facility that we're moving to. We're growing a lot as a company right now. So I'm pretty excited to kind of get our hands on our own hardware. And, you know, there's a lot of like iteration that we can be doing on that much more quickly. Instead of, you know, right now we're working with our collaborators, which is very useful in a lot of ways, but there's nothing like having your own hardware to mess around with. So pretty excited about that. Anyways, thanks everyone. That's all I had for this presentation. Fabio, do you want to keep going?
No, sorry, I kind of got disconnected just for a second, but thanks for giving this. I guess the only thing I'll say is you know, we're hiring. We're looking for interns and full-time people across various teams. So if you know anyone or you're interested.
Yeah, absolutely. Yeah, thanks for reminding me of that, Fabio.
Yeah, we can share that information throughout Stanford and Oxford. Yeah.
Thanks, Merritt. Appreciate that. Yeah, if anyone's interested in working in the lab and getting their hands on hardware, let us know. We have open positions right now.
Okay, so I guess we can take questions now. I actually have a question. I have a clarification question. So I don't have a background in hardware, but from what I can tell, it's really hard to physically make stuff. And I'm understanding Bleximo's approach is kind of anti-hardware agnostic, where it's like you have specific problems. So I think you start from a problem and then you co-design the hardware and software together specific to that problem. But each of these problems have different specific requirements. So how do you identify the problems themselves? Let's say I'm like I have an optimization problem, let's say, and then Jeremiah wants to do derivatives pricing. So he wants to do some quantum Monte Carlo stuff. And then another researcher wants to do machine learning stuff. So how do you choose? Let's say you have these 3 clients. I'm assuming that you are going to work with clients you're going to offer some consulting or build stuff according to them. Or do you identify problems yourself? So how do you decide what to build? That's my question.
It's a great question for Fabio, maybe. You know, a lot of it has to do with.
So the problem is I lost half the question.
Oh.
Okay.
Yeah.
Sorry. Yeah. Do you want me to repeat, Fabio? So like there are so many different problems, and wait, I think we lost you. Are you here still?
I'm here, but I turned off my video so that hopefully it's more stable for me.
So the question is, there are so many different problems, and you are problem specific. You design your algos and hardware according to these different problems. How do you identify what problems to attack, and is it more client based, or do you decide do you make these decisions internally?
Yeah, so the short answer is that it's client based, but even within a certain client, right, they'll have multiple problems. And then you know, it's to some extent, you know, we give them a recommendation about which problems make sense to work on the most. But okay, outside of clients, we also have kind of, let's say, internal R&D, and that goes for hardware design and for applications, essentially, for algorithms, compilation.
Okay, I think we're losing you.
I would say our internal design thing. Oh, sorry. Can you hear me at all?
Yeah.
Yeah, we lost you at compilation.
We lost you at compilation.
Oh, okay. So I guess the short version is, you know, internal R&D would be, you know, we work at lower level things, and then, you know, for higher level, which applications to focus on, that's client driven. But of course, you know, certain applications are just not near term. And, if a client really wants to work on that, that's not a problem. I mean, we would let them know anyway. But if they want to work on that, we can, work on improving that application as much as possible. But we would probably suggest working on something for which, it's sufficiently hard classically that a smaller instance is already pretty hard to solve. And there are problems like that.
Okay. I see, but still, I mean, I'm still confused
I don't
about
know if
how
my
that.
connection is too bad.
No, we could hear you, but I'm just still trying to understand how that would scale, because if there are you have 5 different problems, how are you going to tackle all 5 different, if they all require different hardware requirements, and how different, or do you kind of
Yeah.
Maybe I'll chime in here for a second. Maybe it's worth distinguishing.
That's a great question.
Oh,
yeah,
using Fabio again. Sorry, Fabio. I just want to chime in real quick. Maybe it's worth distinguishing between the different kinds of hardware. So the hardware that I just gave you guys a presentation on is mechanical hardware, and that is pretty standard across all the systems, or at least we try to make it as standard as we can. The only thing that does change is the way that the RF lines are arranged and the different types of filters and isolators and things like that that are in the system. And we do have brackets that are kind of standardized for each one that you kind of mix and match and put on a modular system for that. But then there's other levels of hardware. There's sort of the PCB level, which is sort of bridging halfway between these big hunks of metal on the mechanical side and the chip. And the design that happens at the chip is more microfab hardware. So you're talking about layers of materials. And so when it comes to PCB and microfab level hardware, that is always co-designed very closely with what maybe you want to simulate the aspirin molecule today. You're going to be working really closely to make sure that PCB and that chip are well suited to that problem, but it's all going to go into the same big hunks of metal that I just showed you earlier. We spend a lot of time making sure that the designs are fully modular as much as possible.
I see, and that's stable, right? The big chunk, and then you have modular parts that can go in and out, and then at the micro level you can also co-design that with the algos, and that's flexible.
Yep. And maybe I can show you guys you see these this part right here that has all the holes in it. We call these the breadboards, and you can see here actually the breadboards have a lot of different RF components bolted onto them, and you see this whole spaghetti of cables connecting them. So let's say you bring in a 4-qubit chip that needs 4 filtering lines. You bolt on one of these gangs of filters onto your breadboard, but then the next day you need an 8-qubit chip. You bolt on another one of those onto the breadboard, and just kind of mix and match whatever kind of RF components you need for that particular cooldown. So in that sense, the mechanical hardware is kind of one size fits all as much as we can make it. But the chip and the PCB, there's all kinds of RF magic happening in there that doesn't really work very well. As Fabio kind of pointed out, it doesn't really work very well when you're trying to run on very sparse resources in the Nisk era. So
got it. Okay, thanks.
Yeah, so the short version of this is that the fab of the chip and the even chip design, that's not something that will likely be fully scalable, to the sense that there's not going to be a SaaS solution that produces a chip for you, at least maybe not in the next few years. That's sort of labor intensive, and so of course the company's resources, that does mean that to some extent we can't work on every single problem. There is some prioritization that happens.
Yeah. Okay. And that's decided internally through R&D, I guess.
Yeah.
Okay, cool, very cool. Any more questions?
Yeah, I have a very specific question actually. Wait, can you, in your presentation, there was something, I think it was, yeah, on one of the slide, on like a couple of slides, like there was this thing called like TWPA. Can you explain what that is?
Yeah, a traveling wave parametric amplifier. It's a little bit beyond my wheelhouse to tell you exactly why we need it, why why it looks the way it does. But from my perspective as a mechanical guy, it's a super expensive, super special RF component that comes from Lincoln Labs at MIT, and it's very important for getting high quality signals into the qubits. Maybe Fabio can talk more about that. I don't know.
Nope, that's my limit there too.
Oh, so it's more for like input than as opposed to output. Like, does it help in like sending the right signals to qubits, or does it help in like reading out qubit measurements?
That's a good
in
question.
principle,
I think
both.
Oh, okay.
Go ahead, Fabio. Yeah.
No, that's, I mean, it's just, it's kind of a control component. So it's not like one or the other necessarily. There's different schemes that one could use it for. That much I know.
Tupas are pretty special objects that we put in the fridge. Anecdotally, I know that they're quite like painful to make from a microfabrication standpoint, and they don't last long unless they're stored under vacuum conditions. So one of the big sort of pushes with this design, here, I'll show this slide here. One of the big pushes with this design is making sure that you can keep these tupas in the fridge, like on this flange that you see here on the bottom right. You can keep the tupa in the fridge without ever having to take them out, and you can still access the ports to like swap out different lines going in and out of the tupa without having to like remove the whole box itself and expose it to atmospheric pressure. Apparently they have like a limited shelf life measured in like weeks and months, unless you're keeping them under high vacuum. So this design was all about making sure that they're well shielded, well thermalized, and never really have to be taken out of the fridge any more than they have to. It's very easy to swap out lines. So you see on the bottom of this flange, there's those little ports. And you just look underneath on the fridge to get at those ports. You don't have to like take the shields off or anything. Does that help you at all, Siddharth?
Yeah, thanks a lot.
Any more questions?
I had a question, I guess, on I'm trying to think how to phrase this. Like, I guess there are currently other startups, use like software startups, I guess, and like their mentality or approach for like application quantum algorithms, a focus on algorithms is that like they'll take some algorithm and they will then try to find the best like hardware, like cloud source hardware, and then like redesign the algorithm and have new error mitigation techniques to get like the best results. Obviously, your approach is more like we're gonna do this plus like the hardware, optimize the hardware so you can like improve like change T1's connectivity, etc. Is there any way like to like quantify, maybe even just like qualitatively describe how your approach would be better than just like a software approach?
Well, so yes, to some extent. Like with a software approach, you're kind of limited to the hardware platforms that are already there that are generic hardware, right? That's not to say we can't partner with software vendors, right? Like we absolutely can. We're a hardware company. It's just that the choices we make in building hardware are kind of guided by specific algorithms. So to some extent, by coming directly to us, we can give you like a, as optimized as possible for the hardware given the current technology, right? Like it will be designed for your particular application, using a specific algorithm, and that can be patentable much more straightforwardly than a generic algorithm can, right? So that's actually one advantage for clients. But in addition, we're not working with generic compilers and generic kind of optimal or generic like qubit control techniques, right? So all of that would be kind of optimized for that particular application. So that's the advantage, that you don't have that control as a pure software company. And then what in principle is there, you could spend the resources and kind of go to different hardware providers and go to the qubit level and optimize there. Like if you did that, you would get like maybe 80% of what we do. Because the thing you wouldn't do is maybe design the chip and analyze the chip and all of that. But you could, in principle, design. Qiskit lets you do pulse level control, right? So you could go down there. You could also, design your own error mitigation schemes and all of that. So if you do all that, you do get a lot of what we do. I just, to be honest, haven't seen many software startups do that. They tend to work at a higher level. So that's my answer to that. But if they did go there, then yeah, they would kind of compete in that sense.
That makes sense. Thank you so much.
Mm-hmm.
Okay, I guess we can wrap up. Thanks everyone for coming. Alexi, do you have any closing remarks, or should I close this off?
That was great. I mean, please close it all, but I'm really impressed. Thanks, guys. It was really awesome.
Yeah, we had a really good crowd turnout today. So yeah, thanks everyone for coming. Thanks, Fabio. Thanks, Ziggy. I hope to see you next week then at Q2B. Ziggy, you said you will be there. Fabio, I don't know.
I will be there too, yeah.
Perfect.
Just so we'll have a booth, yeah.
Okay, so then that's 4 or 5 of us, Jamie and Santi as well. Okay, cool. All right. Thanks everyone for coming. Bye-bye.
Thank you. Bye.
Thanks all. See ya.